It's like the first, I know. Normally, I would grab the wrong one every time. It's not even close. There's no question about it. So negative 4.9 t squared plus v sub o t sine theta plus h naught. And so we know that x equals, what did I say? 40 cosine of 30 times t. I'm going to write it like that instead, if you don't mind. I don't care if you do, I'm going to do it anyways. 4.9 t squared plus 40 sine 30 t plus 2. Yes? Now, just for fun, I'm going to do this next step because I enjoy it a little bit. What is the cosine of 30 on your calculator? Cosine of 30 is, what's the matter, Taylor? You're looking at it funny. What's the matter, girl?
What's after the 4.9 squared?
Plus v sub o t sine theta. Or you mean down here? Oh, 40 sine 30? Sorry about that. Yeah, sure. What is the cosine of 30? It's 0.866 or something times 40 is? Okay, what this is saying to us is that our little ball, the picture that I had up here a minute ago that I erased, our little ball is going to go 34 meters, 0.6 meters every second. You with me on this? Now, initially, what is this value here? The sine of 30 is a half, right? Times 40 is 20. But what's going to happen to the ball's velocity in the upward direction as time goes on? It's going to slow down, yes? But the horizontal piece will always be this 34.6. Are you with me? Every second. Okay? So it's going to look something like this, and then it's going to look something like this, and then perhaps the other direction, and then like this, and then down further. Nice? And so the game is, when does she hit the ground? So if it's when it hit the ground, simply just set it equal to 0. This is where I want you to use Desmos. I want you to use Desmos. Boom. And I want you to just simply graph it. I want you to go negative 4.9 x squared plus 20x. That's 220 plus 20x plus 2. Hey, look, when does it hit the ground? Alex, it hits the ground 2 times, sir. Mr. Patterson told me it has 2 zeros. One of them is negative 0.098 seconds. I don't think I want that one. By the way, it never was on the ground because when did time start here? 0. Oh, and when did it happen? Where was it? At time equals 0, it was at a height of 2, yes? It never was on the ground. Right? Now, when did it hit the ground? It hit the ground at 4.179 seconds, yes? You see that? So how far did the ball go in this direction across the ground? How did I figure that out? I think I would subtract. I think I would take the horizontal velocity, which was 34.6, is that right? And I would multiply it by how long did I go at that time? And I said it was what? 4.17? I think. Is that right? 4.179? Yep. And so the ball went 144.5 meters in the x direction. Nice. Now, clearly the ball traveled a lot farther than that distance-wise, yes? Because the ball went from here to here, but the displacement in the x direction is simply from here to here, yes? Nice. We can do it different. Shroom, can we go up on top of a building and do something like this? Yeah, let's do that. So we're going to go up on top. No, let's do this. Our intrepid explorer is on a cruise ship. The cruise ship, which sits like this in the water, 50 meters above the water. And she's up here on the back of it, hitting golf balls into the water, destroying the environment. Thanks. Way to go, kid. We all have to live here, but whatever. We know you're special. 60 meters a second. Really crushing that ball at it, girl. 22-degree angle. Hitting it with her driver there, just crushing the snot out of this ball. Awesome. So, how far behind the ship, you see, will it land? I don't know. We can find out, though, I feel like. So, x equals 60 cosine 22 times t. Again, this is your velocity times time, yes? And then, of course, the other one is negative 4.9 t squared plus 60 sine 22 t. Again, there's your velocity. Plus h naught, which is plus 50. All right. So when would it get out? I don't know, Mr. Groom. I feel like I would set this equal to 0. I would too. Back in my day, which was not the good old days per se, in my day, a fella had to actually do the quadratic formula. I'm not a horrible person. I'm not going to make you do that. That's ridiculous. Because that's just mean. Plus 50, is that right? So the ball is going to be in the air for 3.14 seconds. Well, that's not very long. That's because she hit it basically flat, yes? And so it's basically not going to go up very far. It's basically going to start, it starts falling as soon as she gets rid of it, okay? But it's still going to go up for a short period of time. In fact, if you do this, if you come up here, you will see that, boy, Mr. Grimm, it doesn't go up very much at all. It's basically, if you zoom in on that a little bit, oops, wait, stop. Zoom in. Something screwy there. Negative 4.9, 60 sine 22. Did I miss something there? Negative 4.9, sine 22. Zoom. 50. What is going on there? Why is that not? Oh! That's embarrassing. So my answer was wrong on the previous problem. That blows. Okay. We'll have to jot that down in a minute, okay? We'll fix that momentarily. My bad. Okay, there we go. Do you see what happened, friends? If you're in radians, it's not the right answer. Are you with me? You should probably check yourself, Mr. Groom. Check yourself before you wreck yourself. So, notice it flies for 6.2 seconds. Are you with me? 6.2 seconds. And so 6.2 times 60 cosine 22. This ball travels about 345 meters. Wow, Tiger Woods can't even hit that far. Well, Tiger Woods can't hit that far on the ground. Well, he sucks now. But even a guy who's still good can hit that far because they're hitting it pretty much on a flat ground, a flat surface, yes? Here you've got a 50-meter head start. The thing's got to fly, right? So it's going to go up farther, then it's going to fall farther. So, of course, it's going to fly farther when it's all said and done, okay? So make sure you're in degrees before you do these. Don't be like Mr. Groom. Actually, do something right. By the way, did you notice what happened? When you scrolled up here to 50, it sure looked like her ball started coming down right off the bat. Well, that's weird, okay? Now, is it possible that you could have done that? Yes. She could have stood on the deck and then thrown the ball downward like this, yes? That's fine. That's not what happened. She hit the ball upwards, yes? So the actual graph should look like that. So, yeah. Now, do this with me. What we just did here, this is what's called a parametric. These are called parametric equations. And because they rely on the parameter of time. And let's be honest, in the real world, everything's about time or money. The parameter of time. Think about this. I don't care who you are. You're Mr. Romantic, Mr. Alex Cross here. I'm so romantic. I feel like it's all about love, Mr. Groom. You're wrong. It's not about time. You're wrong. Because if you had somewhere you could go today, well, I would take my girlfriend or my wife or whatever, and we'd fly to Paris for a month, and it would be great. Well, then what's stopping you? Well, only time or money? That's what I thought. Okay? So, yeah, love trumps all as long as you've got the money to pull it off sometimes. Okay, but whatever. Now, Mr. Groom, can Desmos graph them in parametric format? And the answer is yes. So this is how you do it. If you've never done it, you should pay attention to this. It's kind of a big freaking deal. Oops, not F, little f. F of t equals, I said. What was it, 60? No, how hard did you hit it, 60? Cosine 22, t, wait for it. And let's do g of t equal negative 4.9 t squared plus 60 sine 22 t plus 50. Nice. Now do this for me. Bless you. If you do this, parentheses, f of t, g of t, oops, not big G, little g of t. Oh, that's hot, friends. Are you leaving me?
I'm gonna go to the restroom.
Oh, have a good time. All right, goodbye. This black line represents the actual flight of the ball. Notice I hid the x and y components. I didn't want to see the x and y components. I just wanted to see just what the actual ball flight looks like. What's wrong with this picture? Why did the ball just stop? Why did the ball just stop? Look at it. Why do you think it just stopped? Why do you think over there? Why do you think it just stopped? Because that's only for 1 second. You see that right there? That's what happens between 0 and 1. How long was this ball in the air for? Well, I'm going to put it for 4 seconds. Hey, that's cool, but what happens? Oh, it stops again. That sucks. How long was this ball in the air for? 6 something. So if I do 7 seconds, wow, bam, there she goes, yes? The only problem with parametric equations is you can't trace them. But you can get a very good idea of what the path of the ball looks like. Right there. Notice that it hits at a place in time. It hits at a place, yes? This is an x comma y. It's where you want to go pick up the damage, right? This is where the bad guys got hurt when you drop a picnic basket on them or something, okay? This is where ground zero happens. It's not when it happens, where it happens. Because frequently, I need to know when it happens, but most often I kind of need to tell the fireman, hey, look, there's going to be a wreck. There's a wreck at 5 o'clock. That's nice. Can you tell me where? Highway 30. Can you be less specific? Oh, Highway 30, Columbia Boulevard. Oh, thank you. That's all I need to know. Yeah, thanks. Sweet. So then I can actually get there. So time and place. Time is nice, I guess. Place is oftentimes better. Okay, I need to know both, though. So notice here, when I've graphed them, I've, in essence, gotten rid of, I'm still graphing in terms of t, but what I'm actually graphing is just the x's versus the y's. Okay? So it would be really cool if a person could trace this and find out like exactly where it hits the ground. You can't. Now I know what Alex is going. I could just zoom. And if you did, you'd find the same answer we got a few minutes ago when we timed it out, yes? So that's not really helpful. But I enjoy this. This is kind of a neat thing to watch. Back in the day, the only thing the TI calculator will do better than this thing, which is hard to believe, is you used to be able to have, like, you can shoot something from this direction and have an airplane coming by. Whoppa! And you could trace them and animate them at the same time, but I don't think you can do that in Desmos that I've been able to figure out, which kind of sucks. But we'll see what we can do with that. Now, what if you were up here in your airplane? It's World War I. No, wait. Wait for it. Wait for it. Wait for it. Mr. Groom, the Pictionary master. Yeah? Snoopy in his doghouse. There he goes. Now, he's buzzing over the lines. He's buzzing along at, I don't know, 200 meters a second. Because he's just, why wouldn't you? Why wouldn't you be going 500 miles an hour or so in your doghouse? I don't know. And he drops a picnic basket. Yes, that's what he does. A picnic basket to the German soldiers down there behind the enemy lines. Okay? Well, we're not going to drop a bomb. That would be mean. So I feel like we're just going to drop some picnic baskets to them. Now, here's the question. There's the bad guys. Bad guys. Okay? Whatever. That's where their tent is and everything. Now, the question is, where should he release the picnic basket? What would that depend on? I feel like a couple things, yes? What? Well, so I want to know this distance, yes? Because that's what I want to know. But the question is, I think it depends on how fast I'm going, which I know that. What else does it depend on? The altitude, that's right. So he's flying along. He's clearly wearing his gas mask. Clearly. And so he is at a height of, I don't know, 10,000 meters, because why not? Cool. So, this is a very aerodynamic picnic basket. So we're going to ignore wind resistance on it for now. Okay, it's a very aerodynamic picnic basket. Clearly it's going to follow some sort of a path that looks like this, yes? Wappa! Right? Hi, how's it going? How are you?
Okay.
Good. Have a nice day. Does this see? Oh, shit. Wait, stop. He dropped my class. I don't know who he has anymore. All right, cool. So our equations will look something like this. X equals what now? Vt. I'll just go ahead and write them momentarily. And y equals this fella. So I feel like I know, do I know x? I don't feel like I know x, do I? And so I need to find this. So 0 equals negative 4.9 t squared plus 200 sine, oh, what would the angle be here if you're in level flight? Zero. T plus 10,000. Wait a minute. What's the sine of 0? It's 0. Wait a minute, Mr. Groom. If you are flying this direction and you just release something, how much up or down velocity does it have? If you just drop it. If you're flying this way, but you just drop it, how much up or down velocity does it have? 0. Nada. So this piece is going to cancel out, yes? Okay. Now, obviously the other piece is going to be x equals vt, not vt, you dummy, 200. Now, what is the cosine of 0, friends? This one is 1. So in other words, all of the velocity is in the x direction, yes? All of it is in the x direction. So when I do this, take this baby here, set it equal to 0, solve it. Okay, so in Desmos, how could I do that? Well, you could graph it, I suppose, if you're like that. You could graph it and go negative 4.9 x squared plus 10,000. And you'll notice that it hits the ground in 45 seconds, yes? You could also just go equal 0, and Betsy will do it for you. Well, it'll just graph it, but it's still the same deal, yes? It's totally up to you how you want to do it. All right, so 45 seconds it's in the air. How far is this thing going to go in 45 seconds? Well, it's going to go 200 times 45, yes? Which is what? 9d with 2 zeros, 9,000 meters, is that right? It's going to fly 9 kilometers. Wow. So you better make sure that you are good to go and where it's going to be lined up. By the way, this is why back in the day, dropping bombs from very high altitudes at all was a total crapshoot. Because even though you had a picnic basket that was semi-aerodynamic, the winds could hit them and put them off target just really easy. Okay? If you didn't have a very big kaboom when it hits the ground, you might kill some pedestrians or whatever, but you completely missed the actual target that you were shooting for. You know, a horse got blowed up or the Baskin Robbins, but you completely missed the ammunition factory you were trying to blow up. Okay, which sucks because I wanted ice cream today. Okay, but anyway, whatever. So just keep that in mind as you're doing this. Question? Did you have a question, dear? All right. So back in the old days, of course, Snoopy couldn't fly very high because he didn't have oxygen masks. So they had to get down into here. All right. Now you get down to here and you're flying slow. Now someone could pick you off with a machine gun, which wasn't real fun. Yeah. And then the bombs that they carried, they had to be big enough to lift them up out of their cockpit with them and then throw them overboard, which was kind of tricky. So World War I was kind of a god-awful mess, all right? You throw some hand grenades down maybe, but that's about the extent of it. That's why the Germans had the big blimps that could fly, you know, all the way over to Great Britain and bomb them, all right? But you could haul a lot of crap inside your blimp. The problem is they had hydrogen in them, but whatever, that's a minor issue. Now, back in the day, in World War II, however, you saw a lot more of this action. Dive bombing with your picnic basket. All right? Now, what's going to happen with my dive bombing run here? By the way, I don't hit the ship at the water level. I'd like to hit it a little higher up. I don't know what this is. What's this weird? The promenade deck. Aye, aye, Captain. Cool. Now, this boat is something like 30 meters off the water surface there. I don't know why you're driving it out in the open like that, but whatever. This plane's coming in at about 85 meters per second, which is moving right along. For World War II, that's just shy of 200 miles an hour, right at 200 miles an hour, so that's moving okay. Yeah, cool. I can't really put you in both things, but there's two airplanes. Okay, now coming in like so, releasing the bomb like so. All right, so talk to me about this thing. X equals VT cosine theta. Y equals negative 4.9 t squared plus VT sine theta plus H naught. Yeah, look at this, dude. 50-degree dive. How would you put that in, this equation? How would you put it in? In a dive, what would you do? So 85 times the cosine of what? 50? Or negative 50? Negative 50. Now, if you're playing along at home, what is the cosine of negative 50? Do that on your calculator. Oh my gosh, it's positive, just like the cosine of positive 50. Am I right, though? Is it the same as for positive 50? It is. Now, why is that? Well, if you've had any kind of trig at all, in the unit circle, here's 50 degrees, here's 50 degrees. They share the same cosine, don't they? Okay? But, what about the sine? It would be negative 4.9 t squared plus 85 sine negative 50 t plus, oh shoot, what's his altitude? His altitude is 6,000 feet when he drops the, 6,000 meters when he drops the bomb, plus 6,000. Okay? Now, what happens when you take the sine of negative 50? The sine of negative 50 is a negative number, right? And so the idea here is the sine of negative 50, that's because you came down on this one and this one you went up. They have opposite signs on their signs. Yes? And so this one is coming down. Initially it had negative velocity. So give me some numbers. What is this top one? X equals 85 times the cosine of 54.6 t. And then the other one is negative 4.9 t squared plus
Negative 65.
Oh yeah, minus 65 point what? T plus 6,000. And again, set it equal to 0. Set it equal to 0. Find out when this hits the ground, please. What'd you get? What'd you get? What'd you get? So 28.9 seconds. 28.9 seconds is how long it takes to hit the ground. Where does it hit? You plug it back into here. Right? So it's going to be 54 times that 28. About 1,500-ish. That's where you want to get back to drop the bomb from, is back there somewhere. Yes? Almost. Did I forget something? Yeah, the height of the boat. Now watch, what did I do different? Put equal to 30, right? Now by the time the picnic basket has fallen that far, is that going to change my time much? Not much. And so is it going to change my distance much? Nope. And that's why you use a big kaboom in your picnic basket. Because you need to be close. Back in the day. Now we have guided missiles we put through Saddam's window, from 10,000 miles. I'm not joking. Well, he's dead, but I mean somebody's window. They're the guided missiles, right? You can just drive them right through wherever you want to drive them. From sitting in your lawn chair, basically, in Nebraska. Wabba! Yeah, and that's no joke, right? Back in the day, oh, by the way, one of the best movies of all time. I highly recommend you watch it. I remember reading the book, and then I saw the movie one time. I'm like, dude, this is hilarious. It's in the 60s. It's called Dr. Strangelove, or How I Learned to Stop Hating the Bomb and Learn to Love It, or something like this. And so Peter Sellers is the actor in the movie. He plays the president. He plays this crazy wheelchair-bound scientist who invented the nuclear weapons. He plays like 4 parts in the movie. It's just hilarious. Anyway, Dr. Strangelove, he's this guy in a chair. He's like moving his arms all spastically, like it just controls itself and stuff. Anyway, so something happened. And the computers say that Russia launched an attack on us. So we've scrambled all our bombers. And they get able to get hold of all but one of the bombers. And so it's Slim Pickens. This guy used to be in all these cowboy pictures. He's the commander of the bomb wing and whatever. So they're going to go bomb the Ruskies. We're going to bomb them anyway. That's hilarious. Anyway, they go to open the bomb door because you have to fly the B-52 all the way across Russia and not get shot down, which is kind of tricky. Anyway, so he's going to release the bomb. And of course, they couldn't get to their first bomb target. They couldn't get to the second bomb target. So finally, the third bomb target was something like a candy factory or something ridiculous. That was literally what they said in the movie. So then the bomb doors wouldn't open. So he gets down there and he sits on it like a bull and finally gets the thing to come loose. And he's riding this bomb all the way down. I highly recommend you watch it. It's the weirdest freaking movie ever, but it's pretty funny. Anyways, the one guy plays like, and George C. Scott's the general. And he's just like, let's go bomb them all. Mr. President, if we launch a strike right now, we'll still have a lot of us will be left. And you're like, what? It's so weird, people. Now, here's a question for you. So if Taylor's going to be teeing off back here. Atta girl. I don't know. I don't draw pictures very good. Wampa. Okay. And she's going to hit it to here like this. That's nice. And we know that this is 300 meters away. And we know that you are launching from 10 meters up. That's nice. By the way, you could put her initial height at 10, or you could put her initial height at 0 and the ball's height at -10, yes? Or the final pin height right here. So here's my question, kid. If you were to launch this sucker thusly at some angle here that's, I don't know, like 20 degrees, how hard would you have to hit it to get to hit right at the pin? What would the velocity need to be? Now let's think about this for a minute. X equals VT cosine theta, and y equals -4.9 t squared plus VT sine theta plus h naught. So what do we know? We know this is 300. We know that's equal to I don't know times I don't know times the cosine of 20. Can you solve for two equations? You can if you sorry, you didn't let me finish. Can you solve for two unknowns? Not with one equation, but that's good because I have two. Okay? I have two equations, you see. I have this equation here, which also I don't know v and t. And are you with me? It was plus 10, right? Yes? Now can I solve it? You better believe it. Now, if you were back in, I don't know, some time ago, and you were going to do one of these things in class, what would Mr. So-and-so or whoever tell you to do to solve an equation like this? You have two equations with two unknowns. How do you solve them? I put in a decimal. Sorry, it doesn't work that way. Okay, take another answer. Well, I graph it. Well, put them equal to each other. Well, you'd have to have something equal in both of them. That'd be tricky, though, right? If I could, that'd be great. But you know they both have t's in them? Yes, but you'd have to solve for this one for t, which is going to be gross, and solve this one for t, which wouldn't be too bad. That feels weird, okay? But I like that idea. Could I, up here, solve for t? Or b, either one, yes? I think I want to solve for, now wait, if I solve this equation here for t, I would get t equals 300 over v, v cosine 20. I could do that. Here's my problem with that, though. I'd have to plug that in here and here, yes? But what if I, instead of solving for t, what if I solve for v instead? So v would equal 300 over t cosine 20, yes? And now my substitution is easier because now I get this. Times t times the sine of 20 plus 10. Before we go any further, what happens to these t's right here? There's a t on the top and the bottom. Oh, that's nice. They cancel off. Wait! I see sine over cosine. What is sine over cosine? What is sine divided by cosine, people? People? Wait. Here's a triangle. Yes? Yes? Are you with me? Here's my angle. Yes? A, B, C, let's say. So you know that the cosine of theta is B over C, right? And you know the sine of theta is A over C, yes? So what would sine over cosine be? Well, it would be A over C over B over C, which is, of course, A over C times C over B, which is A over B, which is what of theta? Tangent. Nice. So this equation then becomes this. And you thought you'd never use that crap. 300 tangent 20 plus what? Plus 10. So notice, I can solve this bottom equation for the t right here by graphing. And then I can plug it back in up here and find the velocity that I need to pull this off. Let's try that. Okay. You will do that a bunch. It's the same thing, however, right? Typically, if you need to solve for v, you're going to solve for t at the same time. Totally up to you, though. Look bored. I'm sorry, though. I really had something that I wanted to talk. I really had something I swear that I wanted you to do for me, but now I can't remember what it is. It's all right. I'll get over it. So what'd you get down here for the answer down here? 11 points. That feels too big. I don't know. I mean, I know she's a hitter and all.
4.9. I was in.
4.9 seconds. I'd buy that for a nickel. Now, if you plug 4.9 seconds in up here, but remember, this is where classic rookies will screw this up sometimes. Now, in Desmos, it's hard because Desmos, if you once you hit divide by, it keeps everything in the basement until you can tell it otherwise. But if you're using a regular calculator, 4.9 times the cosine of 20, whatever that number comes out to be, and then 300 divided by that whole shebang. Yeah. 65 meters a second. 65 meters per second. Now, let's think about that. Does that make sense? I think so. If the ball is in the air for basically 5 seconds, and you hit it at 65 meters a second, 65 times 5, well, that's a little more, right, than 300 meters, yes? But that's because not all of it was in the x direction, was it? Right? You barely hit it up, just not too high, right? Most of it is out, not so much of it is up. If I wanted to check myself, this is a time where Desmos, I think, is kind of neat to do that with the parametric equations. Equals, what was it? 60, what did you say, 65? And then cosine of 22t. And g of t equal negative 4.9 t squared plus 65 sine 22, t plus 10. And then, of course, down here, parentheses, f of t, comma, g of t. That's hot. And you said it was for like 6 seconds or something. Oh, look at that. How far did it travel? So it looks like it went 300 and some meters. Yes? How far was it supposed to travel? 300. Interesting. 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 That means somebody's calculations were a skosh off. Oh, is it 20? Oh, that's my bad. Well, somebody screwed up. Figures it's me. Now is it hit 300? Nice. So the 22, I hit it up a little higher in that situation, yes? So it was able to fall for longer. Therefore, it was able to get there, yes? Keep in mind, as Buzz Lightyear once said, right? It's falling with style. Yeah, no, that wasn't Buzz who said that. That was Woody. Yeah, Woody said that about Buzz, right? It's falling with grace. Falling with style? Who said that? Was it falling with style? Yeah, right. Yeah, so, you know, so Buzz jumps off of the dresser over here or whatever. Yeah, whatever, with his helmet on and stuff. And hits the bowling ball or something, or not bowling ball, beach ball or something. Blue! He creates himself into a projectile, yes? Please understand that this does not work for things that are powered flight at all. Please understand that this kind of works kind of works if you talk about a muzzle loader. It is not rifled at all. Rifled stuff acts a little differently. And also, please understand that in baseball, you're like, I was watching the other day, Mr. Groom, and Giancarlo Stanton hit one with a launch angle of whatever and this and that. And if you watch the flight of the ball, it actually does this. It tends to fly like this. That's because you cannot really neglect air resistance. Okay, we can talk like we can, and at low speeds we can. But as you start doing this number, it starts slowing down in this direction too, yes? And that is why as you go in this way, it tends to start falling steeper because it's not falling at the same rate, or it's not going this direction at the same rate as it was before. For years we always taught kids, well, we lie to children all the time, let's be honest with you. We always said, hey, look, it's parabolic. Well, not quite. Turns out there's a parabola, and at the end of our parabola, there is some sort of an e to the minus t kind of an aspect of it. So as time goes on, this thing gets closer and closer to zero, and it tends to kind of down like so. Okay? And so we'll see that maybe a little bit. We might look at some actual data from that kind of thing. Hard to see that in a classroom, launching a little ball like so, yes? Kind of hard to see that because it's not going hard enough or fast enough to get much of an air resistance. So in a classroom, we can just neglect it and be hunky-dory for the most part, okay? But if you were designing a bomb or something to drop like that, one would want to make sure they do a better job of it. What time is this class over? All right, I'm done talking now. All right.